Right. Today we're going to study comparison tests because sometimes it's very difficult to use the integral test to prove it's convergent or divergent. Why comparison test is useful? Since we already know that given a series, if the term or the non-negative, positive, consider, n start from n to infinity an, right? And here if an all positive, you only have two results, either divergent to infinity, either it's divergent to infinity, and yeah, this is stupid. I bought one much better than this project. I can use that in the daylight. All right, so this is so you can only have it if you look at the partial sum, okay? The partial sum is n case from n to ak, right? So this partial sum will be increasing. So you only do it if it's bounded, then it convergent to a finite number. If it's not bounded, it'll be infinite. So only two cases, either finite or finite number. That's only two cases. Goes to that direction. Okay. So in this case, we say it's divergent. In this case, we say it's convergent to the series. Okay. Right. So now if we have n less than or equal to bn, they're all both positive, right? Then what you can have? Well, you can look at n is greater than or equal to k, greater than capital N. Then this one is less than or equal to, right? Okay, so you have this. It's always true, right? Then you pass to the limit. You pass to the limit, then you have this inequality. The limit always exists, either infinite or finite, right? So you can pass to the limit. You cannot say when. Now it's possible the limit is infinite, okay? But this is going to be greater than or equal to 0, I know. So what you can say, if the one on the right-hand side is infinite, then it pushes one on the right-hand side infinite, right? So that you can. This is a conclusion. Okay, if it is infinite, then it pushes the one on the right-hand side is infinite because it's greater than or equal to infinite, right? But if the one on the right-hand side is finite, then the one on the left-hand side is finite. Okay, just because it's controlled by that. It will be very useful comparison theorem. Okay. How useful it is. For example, you want to check whether this is going to be convergent, right? Now, sometimes I even put n here, just n squared plus 1. Of course, you can use an integral test to check, but then it involves the integral of, right? If that you have to think about this integral, then say, okay, I know it's arctangent x. That's fine. Okay, you can use the integral test to check its convergence, but you can also use the comparison test because this looks like almost the 1 over n squared, right? So this is an an. It's going to be less than or equal to 1 over n squared, which is a bn, right? But bn, it's easy to handle. We already know that when it's convergent or not. So that's why you can have this in code, right? But this is a finite. Why it's finite? Because P-series test, right? P-series, P is greater than 1, okay? We already know that. So integral test is useful. You can show that this P-series is convergent. But you can use that to check the very more complicated series. So this implies the one on the right hand side, because when on the right hand side, this one, the limit is finite or is infinite, because this is bounded by some finite number. Of course, this implies this is convergent. Okay, and you can say that by the comparison test. Okay, so we should always mention which one you're talking about, comparison test. Okay, I already gave the argument. If you don't want to give an argument, then you have to mention by the comparison test. Okay, comparison test. All right. But this problem can be proved that it's convergent using integral test again, because you can still find the integral of 1 over x squared plus 1. How about, how about 1 over n squared plus square n? Then you have trouble. Yeah, I don't think you can find evaluate the integral of this. So in this case, my question is, can you, right? Can you evaluate? You cannot. You still have to use the integral, a comparison test for the integral, improper integral. Then it's the same story, right? So what you do is, the nth term is going to be less than or equal to 1 over n squared again. So you need some knowledge in mathematics to do this kind of problem. You have to do some rough estimate. That's a skill you should have. That is a place where you have trouble. Okay, you can find a formula to evaluate the integral, but how can I modify the function to the one I really want? Okay, and make sure the inequality is correct. You cannot just simply drop some terms. If I change the square n to a positive square n to negative square n, then you cannot do the problem like that. Okay, so anyway, this is the same story, and then n start from 1, right? It's less than or equal to it's going to be bn, right? And the bn is a finite, right? So that implies it's convergent. So it is convergent. So this implies it is convergent. But how about this problem? Let's start from n squared. Now, you can use the integral test. Why this is convergent? You think it's convergent, right? But how do you prove that it's convergent? It's very difficult to use a comparison test to prove it's convergent. But you still have knowledge to prove it's convergent. You can use the integral test. Okay, because n squared minus n, you can evaluate the integral. Okay, you can evaluate the integral. First of all, it's clear that f of x equals x squared 1 over x, right? Anyway, this is decreasing, clear. on the interval from 2 to infinity, right? No problem. And then the integral of this function, right? You can evaluate by partial fraction, right? So you can change it to, I just directly write down so it takes times, okay? So this is going to be the function. Okay, then you evaluate its absolute value. It's actually positive when x is positive. So evaluate 2 and the point. And that is going to be x minus 1 over x. And the natural log of b minus 1 over b minus natural log of 2 to 1 over 2. Okay? Now, clearly, when big approaches infinity, this approaches, what is it? Okay? When b approaches infinity, natural log of that approaches 1, which is 0. 0 minus, yeah, it approaches negative 1/2. It's going to be positive natural log of 2. Okay? As b approaches infinity. So in other words, the integral of this function is going to be natural log of 2. Okay? So find it. So this implies the series is convergent. Okay? You can also estimate the answer. You can estimate it. But you can estimate the value, not only convergent. And estimate the value is going to be estimate of the value is going to be it's between the 2 integrals and the first term. Yeah. So this is a estimate n from capital N to infinity is less than equal to. Okay, so in our case, it's natural log of 2. And when n equals 2, 1/2. Yeah, it's pretty good. So you can use the integral test to prove this convergent. Not only that, you can estimate. But it's complicated, right? You have to deal with the function. Sometimes you're lucky you can evaluate the integral of the function. So we go back to n. Can I get something like that? So I have to get the upper bound because I know it's going to be convergent. Okay, based on my experience, n squared is leading term. So the question is, how can I put like some constant divided by n squared, right? So this, you need more skill in mathematics. Okay, so you have to, you have to put some constant, large constant c. Then if we can prove that, you cannot put a c to be 1 because unfortunately n squared minus n is greater than or equal to n squared. You have to change the direction of encoding, okay? Because you drop a negative n, you would increase the denominator, so you get lower bound, but that's useless because you have to prove the sigma of this is finite, but the lower bound of finite does not imply it is finite. Okay, this will be useless. Okay, this useless estimate. Okay, so you have to get the upper bound so that the upper bound is finite. You put a sigma there, right? Now you want to get something, you want to get something like this, it's a finite, right? Then you can say this is a finite. So the question is, how do you find the C? You can make a larger C. I think it works. Okay. How about this? Just assume n squared minus n less than 2c or 4c. Okay. Yeah, let's use 2c and square. Maybe that works. Okay. For some largest n. Yeah, we multiply this. Okay. Let's see. This is equivalent to, right? It's 2n squared minus 2n. And this is equivalent to 2n less than or equal to n squared, right? That's equivalent to 2 less than or equal to n. Great. Okay. So that means when n is greater than or equal to 2, the above inequality holds. Clear? Yes. Okay. So that's all we need. So now we know, but you see how difficult it is, right? I don't think not everybody in this classroom can do like find this nice after above. Simple but double. You know, you have to make a large number. Okay. Okay. Then it implies n star from 2 is less than or equal to, okay, it's going to be finite. This is by the P series. Right? We call the P series, maybe you can say P series test that P is greater than 2, greater than 1. P equals 2 greater than 1, because we know it's greater than 1, it's convergent. All right? So comparison test works, but you have to find out, first of all, make a conjecture whether it's convergent or not. If it's convergent, you have to find the upper bound, simple upper bound. If you want to prove it's divergent, you have to find a nice lower bound. So the lower bound goes to infinity, then push the other side goes, go to infinity. Okay. So that is we will find another nice way to figure out this later. Okay. Yeah, there are many tricks there you can try, and let's do the exercise from the book, or the even number problems. Okay, and this is a I think it's gonna be divergent because I know 1 of n, this is a divergent. Okay, why? The P series, P is greater or equal to 1/2, less than 1, right? I know that. The question, how can I compare? So in other words, I have to put this 1 over square n on the right hand side. I want to see if this is less than or equal to that, right? If that works, then the left hand side is infinity, then the right hand side must be infinity, right? And I think this is true, right? Because it's -1. N squared n minus 1. This holds for n greater than or equal to 2, no problem. Okay, so then this clearly, I should say clearly, right? Clearly. Okay, so then you put the integral, put the infinite sum on both sides. Right? But this side is infinite, then push the other side. Got it? 10. Yeah. So this implies, yeah. So this implies divergent. Okay. But if I change to plus n, then you have a trouble. Got it? So let's redo again. Okay. I know it's still divergent. Question is, how can I prove it? Right? It's just divergent. It's not big, plus minus does not essentially change the convergence of the series. Then in order to divergence, then you have to, this should be on the right-hand side, this should be on the left-hand side, but you cannot put the 1 there. You have to make that one smaller, okay? Then make that smaller. So let's put 1/2 or 1/3. Yeah, if 1/2 does not work, and 1/3. That's the idea. That's what I learned from my high school teacher. Okay, I remember. That was the high school training in high school is very important. If you did not learn this math in high school like that, then you have to work hard here. Right? Yeah. All right. Yeah, find the encoding. Okay, let's try this. Okay, I'm not sure it's working. Let's simplify this, right? Multiply both sides, and this will be square n plus 1 less than equal to 2, right? It's the same, you know. And then I see that 1 less than equal to square n. Then I square it. Those are equivalent. It works, right? N is guaranteed because n is greater than equal to 2 actually, or 1. So it's always like that. Okay, great. So maybe my series usually begin with 1. No, that doesn't matter, okay? Because right now square n plus 1 is defined. It's not going to be 0. All right. So that means the above inequality holds for n greater than equal to 1. Then you have this inequality, and I know this is going to be infinite, and you still have the problem. Okay. Okay. So that implies it is divergent. Right. Okay. Let's try next problem. Hi. Who can tell me? It's divergent or convergent? By the way, who is online? Convergent or divergent? Yes? Yeah? Divergent. Just guess? No. 1 over infinity. 1 over infinity. You see, n to the power n, this is a really very giant number when n is large, right? It's much, much larger than n squared. So it decays very, very fast. That's why each additional contribution to the sum is almost can be neglected. And that's what should be convergent. Okay? So you have to use a comparison to compare, because what I'm comparing is I know this is a convergent, right? This is a finite. Okay, I know that. So, but that 1 over n squared decays pretty fast, but not that great, not faster than the 1 over n to the power n. Okay, so it's obvious n to the n is greater than equal to n squared, right? When n is greater than equal to 2, clear? If you turn upside down, clear? Yeah, that's the trick. Okay, so if n start from 2, you always have this, but this is always finite. So that's what pushes the line. Okay. Then yes. So now it's convergent. Okay. If this is a convergent, and then n start from 1 is also convergent, right? Because if n start to 1, it's going to be 1 over 1 to 1 plus n start from 2. So this is a convergent. Okay, it's a finite. So I think this is a difficult part, to prove it's convergent. You have to give me the reason. You cannot say I say it's convergent or whatever. You have to show the argument. Right? And you have to modify as a function to the direction where you can simplify that. But if the encode is wrong, then the answer is wrong. So you have to make sure when you put an encode, you have to make sure why this encode is correct. Okay. But since it's hard to do the estimate, so here another way to there's another way to check the convergence. Okay, so here's the point. Okay, if it's called the limit comparison test. Okay, so you have n greater than or equals 0, bn greater than or equals 0. I'm going to n divided by bn. I take the limit. Suppose the limit exists, right? But bn is simpler. Okay. And at this moment, I just assume L is a finite, okay? It's a finite. Then you will see, where's my file? Okay. Then what you can see that is n and the bn is less than or equal to, because the limit is L, so it's less than 2L for larger n, right? So that means n is always bounded by that. Okay. That means if bn is convergent, then n is convergent. Okay. So n is controlled by bn. Okay. So that means right. So that means if n is convergent, then if bn is convergent, then n is convergent. So that includes that. This is the argument. I already gave you the argument, right? So you can ignore that part, but then where's my file? Okay. So yeah, you find the simple bn. You take the limit, and the L limit is L, right? Then you will get control by this, right? Bn. So if this is finite, then you also get this one finite because above the above encoded. Okay, so that's the argument. Okay. Yeah, let me state this. Yeah, let me restate the theorem. Okay, n greater than or equals 0, bn equals 0, greater than 0. Okay, and then the limit exists. Could be 0. Okay, it's as long as it's finite. And this is a finite. Okay, if then n is finite. Okay. Yeah, n starts from some capital N to infinity. And this is a comparison set. Comparison theorem just in one direction. Now, there's another version is L is positive between 0 and the infinity. Then the convergence are equivalent. Okay, this is a version 1, the first version. The second version is n positive, bn is positive. Okay, and the limit exists. But this L is between 0 and the 1, 0 and the infinity, okay? It's a positive finite number. Then this convergence are equivalent. If and only if there's a difference, small difference here. Why it's convergent is, first of all, yeah, Bn is finite, implies n, sigma n is finite. Okay, but the y converse is true because you can turn this upside down, and then you can, yeah, this implies the limit Bn over n is going to be 1 over L. Okay, because L is positive. So that's why it's a finite. So that's why if the n convergent implies Bn convergent. Okay, so these two are equivalent as long as L is a number between 0 and 1. But sometimes the limit is 0, then you can only have the above one. Okay, if L could be 0, when the L is 0, then you can only show one direction. Right now it's both. Okay, so let's look at the problems again. I'm going back to go back to this square on Shen. Okay, so this is my n. Okay, I want to compare with n 1 over n squared. So Bn is going to be 1 over n squared. So now I'm going to look at the ratio. Okay, so the ratio, if you simplify it, this is almost equal to 1. It's going to be n squared over n squared minus n. It's divided by n. Okay, divided by n squared. How to find the limit? It's going to be 1 over 1 minus 1 over n. So it's going to be 1. Okay, so 1 is between 0. It's positive, finite number. So the convergence are similar. They're the same. So we know that this is going to be finite by p-series test. Okay, so this is finite by p-series test because p is equal to. So that implies sigma n is finite because those two converge. It's the same. Yeah, it implies actually the equivalent. Okay. Just because they're limited. Nearby infinity, those two terms are almost the same. N over Bn is going to be that, right? So you check whether it's convergent. You just needed to look at the leading terms. Then you solve the problem. For example, number 18, I can tell you immediately this is going to be divergent. Right? Why it's divergent? Just drop the constant term. Right? And right? If you take square n out, so this term is almost equal to 1. Okay, so then you just use a bn. Right? So drop on unnecessary terms. Then you compare that. Okay? The limit is always equal 1 if you're doing like that. So the convergence of n, sigma n, is the same as the convergence of sigma bn. So we know it's guaranteed n over bn is going to be always 1. Right? Okay? Since n starts from 1 to infinity, this is a infinite by the p-series test. P equals 1/2, it's less than 1. Then you can conclude. The n, sigma n, is going to be fine. The reason is, I already explained to you, the reason is, you can compare. Let me explain to you directly. Yes, I understand it. Yeah, then this implies is also finite, infinite, okay, by the limit comparison test. Right. Otherwise, if you don't say that, you have to give a proof. Why? Okay. Now let me give you the proof again. Okay. Understand the limit comparison test. The limit of n over bn is going to be 1. So that means n over bn is going to be less than 2, greater than 1/2 for large n, right? We don't know for what capital N, but I know for sufficient large n this is true, because otherwise the limit is not going to be 1. Okay, so that means n is less than or equal to bn, greater than or equal to 1/2 bn. Okay, then you put a sigma for this large n, because the convergence is independent of the first 2 terms. Okay, so now clearly, if one of this is finite, then the other one must be finite. When one of this is infinity, the other one must be infinity. So this is, I know it's a finite, and this is a finite. So the middle one must be finite. Okay, that's the idea. But you don't need to repeat this argument over and over again. You just say by the limit comparison test. That's what you have to mention, limit comparison test. Okay, limit comparison test contains the idea of the proofs. Okay, but you don't need to rewrite over and over again. Just like when you write a program, right? You write a small program, put it there, and use it. You don't need it repeatedly. Of course, you can copy it here to make the program very long. But it's okay, just like make the argument very long, but you don't need to waste time to do that. All right. So just call that test, called limit comparison test. Okay. Otherwise, you have to repeat. This is a limit comparison test details argument, but you don't need to record this. But anyway, understand the argument, understand the limit comparison test is very important, because you know the idea why this works. So that helps you to deal with some strange problems. You cannot quickly call some tests to check the convergence. So you do need to understand the material, the proof for those comparison tests or for those tests. So in order to call them using, okay? When you write a program, you really needed to understand the short program you put there, or somebody already wrote. Yeah, otherwise it's harder to modify, harder to use it. Okay. All right, so number 24. All right, this one. All right, first of all, you see n compares to 3 to the n is nothing. So this can be ignored, okay? So this is an n plus 3 to the n plus 2 to the n. This can be ignored, it's 0, okay? And that's your bn. You can quickly get that. And compare with 3 to the n or 2 to the n. This can be very small. You can also get that using using another way. You know, you can say I'm going to take 3 to the n out. Then it's going to be n over 3 to the n plus 1. Here's n to the 2 to the n plus 1, right? But that part is almost equal 1. So this goes to 1, right? Yeah, it's 0 plus 1 over 0 plus 1. So that's why bn is okay. But bn clearly, yeah. Then you take a look at the limit n over bn. Clearly, it's going to be 1. Right? You don't need to check. It's obvious. Okay. So that means the convergence of sigma n and the convergence of sigma bn are equivalent. Okay. So this is a finite n star from n, and the convergence is the same. Okay. So you can say it's finite or infinite. This is a, yeah, it's equivalent to, okay. Those two are equivalent. So, but it's easy to see from a BA. Okay. So note that right? But clearly this is infinite. Why? Because I equals 3 over 2, it's geometric series, it's greater than 1. So it's divergent. So that implies the other one is divergent. Okay, but it's harder to use a comparison test directly. It's harder to compare and then BN directly. Okay, it's not easy. So you have to use the limit comparison test. Okay, so this implies, yeah, this implies, now we already solved the problem, it's divergent. Okay, so we conclude that it's divergent. One more problem. All right, so how about this? Yeah, the numerator is increasing pretty fast, but I already told you, we know that natural log of n is much slower than any power function. It's much slow. A to the n is greater than 1. It's much slower to n factorial. It's much slower to the n to the n power. Okay, so I'm pretty sure they're not at the same scale when they're grouped. So n factorial over n to the power n decays very fast. So this should be convergent. The question is how do you prove it's convergent? Okay, how to prove it's convergent? Limit the, you have to find the bn, right? Compare, limit the comparison test of comparison, you have to find the bn. I think we have to use the comparison test here. Okay, so n is n over factor, right? So let's write down. It's 1 times 2 times 3 all the way to n. Here's n, right? I need the 1 over n squared, so I actually cut this part. That's enough. But this part is always less than or equal to 1. If n is greater than or equal to 3. How about that, right? If n is greater than or equal to 3, you see, every number under the numerator, right, is larger than the numerator. So each term, those are the numbers less than or equal to 1. So that's going to be less than or equal to 2 over n squared. That's my Bn. This is a trick. Yeah. Right, and oops. Something wrong. Okay. Right, so now we have this comparison. So we know that's for, so when n is greater than 3, right, and you have, yeah, and that is going to be finite just because it's by p-series test. It's going to be finite. Okay, so then we are done with the problem. Can we use a limit comparison? You still have to find the limit, right? Yeah, you have to figure it out like a Bn. Okay, so if you look at the limit comparison, you have n over Bn for that Bn. Okay, so you have to check n. It's going to be n factorial of n to the power n, and here is 2 over n squared. And that limit is going to be 0. Okay, that's going to be limit is going to be 0. But you still have to, yeah, you have to find out it's n factorial over n to the nth power and n squared over 2. Yes, you still need some kind of ideas to prove this limit is going to be 0. Okay, this limit is going to be 0. Okay, why it's 0? Then you have to look at n greater than or equal to, why is 0? It's not going to be 1, okay? So why it's 0? Because n factorial of n to the nth power, you needed to write down all these terms, 1, 2, 3, 4, 5 to the n, and this is n, and then n squared over 2. So in order to make sure this is going to be 0, I need a 3 n cubed in the denominator, right? The same idea. So this is when n is greater than or equal to 4, and this is going to be less than or equal to 6 over n cubed. And after you simplify, 3 over n. And that's why it goes to 0, okay? Yeah. But let's stop here today.